I'm Maria Gatu-Johson. I'm a principal research scientist here at the Plasma Science and Fusion Center. And the reason I got into nuclear diagnostics for fusion in the first place was I took a course my senior year in undergrad in energy physics. And the professors developed neutron diagnostics for the jet tokamak, actually, in the UK. And they were looking for new graduate students. So I first did my senior thesis with them for undergrad, and then ended up staying on as a graduate student and actually building a neutron spectrometer for the jet tokamak and running it on a number of experimental campaigns over there. So that was my start, and then I got really into it and ended up continuing here for my postdoc and then as a research scientist. So the high energy density group at the Plasma Science and Fusion Center, it's well, when I started, it was a relatively small group, but I guess we're getting bigger now. It's 5 senior scientists, myself included. I think right now we have 15 graduate students, 2 postdocs, and 3 lab techs who help us with different lab works. And so basically the foundation for the group is development of nuclear diagnostics, and we're starting to get into X-ray diagnostics as well, for high energy density physics at the inertial confinement fusion facilities, the Omega Laser in Rochester in upstate New York, and the National Ignition Facility, or NIF, in Livermore in California. So the group really has been developing detectors for use at those facilities for 30 years now. We're continuously coming up with new ideas, installing them at the facilities, and doing any physics that we can with them. So the goal really is to go after the physics, but we use the diagnostics as the tool to do it. So this lab that we're in right now here at MIT is our diagnostic development lab, which we use both to develop the diagnostics, test analysis techniques, as well as process the data once it comes back from the facilities. So one of my responsibilities is running this lab together with the students in our group. And then I also run a large neutron spectrometer at each of the large facilities, Omega in New York and NIF in California. So the technology is actually based on a neutron spectrometer that was developed in the 90s, again for the jet tokamak in Europe. And one of my predecessors in this group is actually the head of the group right now, Johan Frenje, brought the concept to the ICF world, so inertial confinement fusion from magnetic confinement fusion. And how it works is you have a plastic conversion foil where neutrons from one of the implosions, like this is actually an example target for what will be used on the NIF. You see it looks like a little can. If you turn it on its side, you can see a little fuel pellet on the inside. When we have one of these implosions, you get the fusion reactions going in that tiny little fusion pellet in the center. You get neutrons emitted from there. So you put a conversion foil for this MRS, or magnetic recoil spectrometer, 26 centimeters away at the NIF. So some of the neutrons that are emitted in this implosion reach that conversion foil, and what they do is they knock out deuterons in that conversion foil. So what we're actually detecting with the MRS outside of the large target chamber is the deuterons from this foil, because it's really hard to detect neutrons directly, so you basically have to do some sort of conversion method to be able to count them. So the deuterons that are knocked out from this foil, they are bent through a bending magnet outside of the target chamber center to end up in a different physical location on the detector array depending on their energy. And we use that to reconstruct a recoil deuteron energy spectrum, and from that we infer what the neutron spectrum looked like when it was emitted from the implosion. Again, Johan brought this technology over from the magnetic confinement fusion world to inertial confinement fusion, and really built it and designed it together with the graduate student. The first one was installed at the Omega Laser in 2007. The NIF one was installed in 2010, which is right when I started in this group. So I've been analyzing data from the NIF MRS since 2010, since like the first data came in, and then helping the ignition campaigns on the NIF until they recently were able to, or we, I should say, recently were able to reach ignition, which means more energy out than was delivered to the target.